Let's see what happens when physical forces exceed material limits. When a suspension arm fractures under pressure, the failure is violent, immediate, and expensive. For decades, engineering relied on a sequential loop to prevent these failures. You drafted a design, manufactured a physical prototype, and pushed it to the breaking point in a test lab. When it broke, you went back to the drawing board to redesign it. This graph illustrates the financial reality of that loop. Plotting the cost of change against time in the development cycle shows a steep exponential curve. A design flaw caught on day one costs nearly nothing to fix. That same flaw discovered during physical prototype testing costs significantly more, as materials, tooling, and labor are already committed. Beyond the financial penalty, this reliance on physical models extends the overall project timeline. Every time a part fails in the test lab, the engineering team has to wait for a completely new physical iteration to be machined or cast before they can resume testing. Building your way out of a design problem is a financial and temporal bottleneck. It slows down iteration and limits how thoroughly a team can optimize a product before it goes to market. The alternative is computer-aided engineering, or CAE. This is the process of mathematically evaluating a digital model against the laws of physics before a single piece of metal is ever cut. Early adoption of CAE had a structural flaw. The design work happened in CAD software, while the analysis happened in completely separate CAE software. Engineers had to export, translate, and import files across platforms, which disrupted workflows and often stripped the models of important geometric data. PTC Creo Simulation collapses those two processes into a single environment. Instead of moving data between isolated programs, advanced multi-physics solvers are embedded directly inside the 3D modeling workspace. By keeping design and analysis under one roof, engineers can take a single piece of static geometry and subject it to structural, thermal, and fluid forces simultaneously to predict how the model responds to multiple physical inputs. This flowchart breaks down the universal pipeline required to run a simulation. To get accurate predictive data, an engineer must transition a raw 3D model into a strict mathematical environment through 5 steps. We start with the base geometry. Next is the material phase. The software needs to know exactly what it is testing. The engineer inputs specific values for density, yield strength, and thermal conductivity, so the system understands how the physical matter will behave. Then we define boundary conditions. This means mathematically locking down specific surfaces to act as constraints and applying exact physical loads, like downward force or internal pressure, to mimic real-world interactions. The fourth step is the mesh. Here, the continuous 3D volume is subdivided into thousands of tiny, mathematically solvable geometric elements. Finally, we solve. The underlying algorithms calculate the physical reactions across every single node of that mesh simultaneously, compiling the millions of individual data points into a cohesive result. Whether you are analyzing a bridge supporting heavy traffic or a circuit board radiating heat, this exact logical pipeline forms the foundation for every type of physics analysis inside Creo. Let's apply this pipeline to a specific case study, an isolated automotive suspension assembly. This visual shows a structural analysis in progress. We are evaluating how the suspension handles a sudden, extreme upward force from a wheel impact. As the red arrows push up on the hub, you can see a localized stress heat map blooming across a specific connecting bracket. By calculating exact displacement and safety factors, the system pinpoints the precise coordinates where the applied force exceeds the material's yield strength, causing permanent physical deformation. But surviving a single maximum load is only one metric. Materials degrade over time due to repeated stress, and we need to account for fatigue analysis. Fatigue simulation takes that same structural load and applies it thousands of times in rapid succession. This predicts the exact cycle count a component can endure before invisible microfractures begin to propagate and cause ultimate failure. Used together, structural and fatigue simulations verify that a part can survive its worst-case scenario today and continue to function safely 10 years down the road.
Engineering parts rarely exist in total isolation. They are built to move, connect, and interact as part of broader mechanisms. Motion simulation studies velocity, acceleration, and dynamic forces across sliding or rotating assemblies. Here we see a 2D cross-section of a complex mechanical linkage in motion. The analysis automatically tracks the geometry and flashes bright collision markers at the exact moments where two distinct parts interfere and attempt to occupy the same physical space. Engineers use this dynamic data to adjust the lengths of linkages, clear up interference zones, and ensure forces are distributed evenly across the mechanism during its full range of movement. A bracket might pass every static stress test, but if its dynamic interaction causes the broader assembly to jam, the design fails. Mechanical force is only one variable. Products are also exposed to extreme environmental conditions, like the internal heat of an automotive engine cooling system. This animation demonstrates computational fluid dynamics, or CFD. This tool allows engineers to track the movement, velocity, and pressure of liquids and gases as they flow around and through a product. Notice how the blue and red particle traces map the internal channels of this radiator. By making adjustments to the channel geometry, the particle pathing becomes more streamlined, reducing turbulence and optimizing the overall fluid flow for better energy efficiency. This directly ties into thermal analysis, which evaluates heat transfer and maps temperature distribution across solid components. The fluid data from the CFD study feeds directly into the thermal data. Engineers can see exactly how effectively the liquid coolant extracts heat from the solid engine block, pinpointing lingering hotspots that could cause the metal to warp. Unmanaged heat and fluid pressure will destroy a component just as thoroughly as a physical impact. Rigorous digital validation is required for all of them. In the past, if an analysis revealed a flaw, the engineer had to export the data, manually rebuild the CAD model, re-import it into the analysis tool, and start meshing all over. Creo's real-time simulation capability changes this workflow. Because the solver runs continuously in the background, analysis results update the moment a geometric change is made. If a bracket is showing dangerous stress levels, the engineer can simply drag the surface to increase the material thickness and watch the stress heat map instantly cool from red to green. No manual remeshing required. This real-time feedback loop removes the friction of trial and error, shortening the cycle between conceptual drafting and performance verification. Adopting computer-aided engineering comes with practical constraints. Simulation is an advanced tool, not an automatic fix. Executing large, multi-physics simulations on complex assemblies places a heavy burden on hardware. It requires immense computational power, and highly detailed meshes demand extended processing times to solve accurately. More importantly, simulation operates on the strict principle of garbage in, garbage out. The algorithms can only process what they are given. If an engineer applies an inaccurate load or defines the boundary conditions incorrectly, the software will confidently output a mathematically perfect but completely inaccurate prediction of reality. PTC Creo provides the computational framework, but the accuracy of the output relies heavily on the foundational engineering knowledge of the person setting up the test. The simulation pipeline is becoming increasingly automated through the integration of artificial intelligence and cloud computing. This is a look at generative design. Rather than an engineer testing a single idea, they establish the physical constraints like maximum weight and load capacity, and an AI algorithm autonomously generates dozens of highly optimized, organically shaped variations that all meet the criteria. By integrating these analysis tools directly into the modeling environment, engineering teams reduce the cost of physical prototypes, minimize material waste, ensure structural safety, and accelerate their development cycles. Moving simulation to the start of the design cycle allows it to act as the primary driver for innovation, ensuring safety and efficiency from the first day of development.